I'm Lauren Lead, Senior Advisor here at CSIS, and have been running a series of events looking at the future of rotorcraft that's been generously supported by Bell and Textron, so we're very grateful for that. We wanted to have an event specifically focused on the joint multi-role tech demonstration effort, and we're very fortunate to have been able to assemble all of the competitors for this, for the effort, and are really looking forward to hearing more about everybody's different approaches to this. One of the things that has come up in the discussion of future vertical lift is this concern about re-injecting innovation into the U.S. rotorcraft industrial base, and so I'm really excited to learn more about what all of you are doing and what that represents, both for the future military capability and just for the nation as a whole. So hopefully we'll all walk out of here energized and excited about that. A couple of admin notes to kick this off. If people could turn off ringers, that would be great. For people that are watching on the web, you can email me questions if you would like when we get to the Q&A period at mleed, M-L-E-E-D, at csis.org, or you can tweet at us. You can tweet your questions to at CSIS SEC Dialogue, so CSIS SEC Dialogue, and we can get questions that way as well. For those of you in the audience, when you have questions, if you could raise your hand and we'll bring a mic to you so that we can both capture it for those listening on the web and for the video. If you could wait for that, that'd be great. I'm going to try to run a tight ship so that we can get through all of this and get to the discussion, which I think will be the interesting part. So let me start. I think you all hopefully have longer bios of each of our panelists today, but we're going to kick it off with Dan Bailey, who is the program director of the Joint Multi-Role Tech Demonstration and Future Vertical Lift Program at the Army's Aviation Material Research Development and Engineering Command for the Army, and is passionately invested in this effort and is going to frame how it fits into the Future Vertical Lift initiative more broadly and just sort of where it stands. So, Dan, over to you.
Okay. Well, thanks, Dr. Lee, for hosting this. We appreciate the opportunity to share our message. And I see a lot of familiar faces, so some of this will not necessarily be new, but it is good to set the groundwork and ensure everyone knows what we are doing and what we are not doing. As you said, so I'm the Army's Joint Multi-Role Future Vertical Lift Program Director, and in that hat, I have oversight both on the S&T program called Joint Multi-Role Tech Demonstrator, and we'll talk about that, and the Future Vertical Lift acquisition efforts to set the stage for a program of record. I work collaboratively under both Brigadier General Bob Marion, who's the PEO for aviation for the Army, and Dr. Bill Lewis, who is the Director for Army S&T Development. So if you would go to the next chart there. This sets the stage, really, from Future Vertical Lift all the way to Joint Multi-Role. On 4 June, you actually held a panel here with our Executive Steering Group co-chairs for Future Vertical Lift, so I'm not going to rehash all of that, but it's very important to understand Future Vertical Lift at large to know where Joint Multi-Role Tech Demonstrator fits into it. Both Congress and DoD, of course, are concerned about the vertical lift state, if you will. We've had a aging fleet for some time. Our fleet is based on 70s and 80s technology and configurations mostly. We've had a decade plus of op-tempo and escalating O&S costs on a vertical lift, losses of life. We have capability gaps that are growing in the vertical lift arena. And of course, our industrial base has been doing a fantastic job of keeping our platforms relevant for the warfight through upgrade programs, but we haven't done a series of new design efforts and really to branch into the new capabilities that are out there today. So those concerns obviously take us to FVL, and FVL is all about a long-range investment strategy to replace our current fleet with the next generation of vertical lift aircraft across the Department of Defense. That's an important thought with emphasis on joint, multi-role, and commonality as our key bid stones. We've got significant limitations in our current fleet, as you could expect, right? We have operational effectiveness limitations, gaps that I mentioned earlier, escalating gaps over time, potential adversary overmatch that we're concerned about. But we're also locked into a certain type of sustainment posture. We're locked into a certain type of acquisition strategy. We're locked into this escalating O&S cost growth that we deal with incrementally, but we've never had an opportunity really to start over fresh across the Department of Defense and bring a new fleet to bear that takes innovation into account. So that's what Future Vertical Lift is all about. We want to look at those opportunities and innovations and bring that forward to a next generation vertical lift fleet. We ultimately have 6 elements of our strategy, and you can see those in the red blocks. So we understand that there is a large S&T portfolio out there. We and the Joint Multi-Role Tech Demonstrator do not own that entirely, right? Subsystems, mission systems, all of those efforts are being developed and furthered across the S&T portfolio. What we are focused on the Joint Multi-Role Tech Demonstrator is that system-level opportunity. And so if you go to the next chart, you'll see where our S&T plan for Joint Multi-Role aligns with Future Vertical Lift. The purpose of JMR-TD, just to develop and demonstrate transformation of vertical lift capabilities. You can see that. So it's all about capabilities. It's all about the system-level look at what we have the opportunity to do for our fleet. We're not building prototypes of the FVL solutions. I want to make that clear up front. These aircraft will certainly look different than what we have today, and you'll hear that and see that today. But they're not the prototypes. You know, they're demonstrator aircraft. They have a series of technologies that enable those configurations in a more efficient and cost-effective manner than we've seen in the past. But they're not full-up systems. So they have existing technologies embedded in them as well that we would not probably carry forward to a future vertical lift. So there's still a further development effort to come under a program of record, anticipated program of record. We understand that the key to S&T for this particular effort is to make sure our tools and competencies are really ready for that program of record. So as we build the tools and the competencies both on the government and industry side, what we can forego is that requirements creep that occurs typically after we have a program of record start. So we have the opportunity up front to set the stage, get the competencies and tools correct so that we go into the program of record with our eyes fully open, exactly what we're going to have coming out of that. We don't have to change it in the midstream. We also realize that technology is going to continue to advance over the next 5 to 6 years as we execute Joint Multi-Role Tech Demonstrator. We also recognize that after we initiate and execute the program of record, technology is going to continue to advance. So we certainly do not think that the first go of Future Vertical Lift is the last go. We'll have incremental upgrades as well. So if you go to the next chart, what we're really focused on here under Joint Multi-Role Tech Demonstrator is the backbone. There's 2 facets to that. There's the air vehicle platform itself and the mission system architecture piece. So if you think about the system at large, the subsystems will come from various sources across the industry and our S&T portfolio and acquisition portfolios. What we are focused on the Joint Multi-Role Tech Demonstrator is that platform, the basics, the backbone. Okay, we want to enable a backbone, if you will, that is enduring, robust, affordable, effective over the long haul. So both the air vehicle piece, meaning the configuration or the truck of that new system, and the mission system architecture is our focus. So if you see, we have 2 parts there, the air vehicle mission systems architecture. Both parts started with configuration trades and analysis early on. That was to shape our understanding so that we could then go forward and do some demonstrations. If I focus on the top piece, which is where we're focused today, that's the air vehicle demo. After the configuration trades and analysis, we sent a solicitation out to industry to tell us, based on a set of requirements that we had defined through the configuration trades and analysis, what industry could give us to meet those capabilities. So that's what we're going to talk about today, but I'll focus on the bottom for just a minute. On the Joint Common Architecture, that is an expansion of what you know as Future Airborne Capability Environment, FACE. That FACE standard that has been under the open group for some time, we believe is the right step and the proper path towards an open architecture. Joint Common Architecture puts a wrapper around it. It is, in my mind, the summary of a true, robust, enduring architecture for the future. We want to ensure that the architecture is long-standing. We certainly understand there's going to be subsystems that we will change over time, but we want the architecture to be enduring. So Joint Common Architecture is that path for us. That standard has been under development for some time. It's a model-based approach, And we are days away from publicly announcing the first demo that you see right there in the small block. That initial demo is a concept validation. Out of that validation, then we will enter a longer series of demonstrations over the next 4 to 5 years for the Joint Common Architecture. Back to the air vehicle piece, I would just say that, that what we've seen to date excites us. We're ready to actually start to build some aircraft and fly them, and we certainly think that they're going to bring the capabilities that the warfighter needs.
I have to figure out how to get back to my timer so I can turn it off and it doesn't beep at you. So we're now going to move to discussions from each of the companies here on some more specifics, hopefully at a relatively general level, about the offerings that they're bringing to the table. And there's a lot of variety in the companies that are participating, both in the designs that they're bringing to Tiltrotor, to coaxial rotor designs, at the size of the companies, all kinds of different attributes along which they differ. And so we're excited to learn more about all of them. So we're going to start with, sorry, that was my timer. Figure that out. With Mr. Troy Gaffey, who's the president and chief engineer of AVX, excuse me, AVX Aircraft Company. He's a retired Army aviator and experienced engineer. So, Troy, why don't you talk a little bit about AVX and what they're offering it?
Thank you. May I have the first charts there, Andrew? Okay, this is not the AVX. I'll take a moment and tell you a little about AVX aircraft.
You can brief those if you want.
Yeah, I could. AVX is about, sir?
You could do well briefing that.
I can work the tilt rotor, yes. AVX is a company that was founded about 9 years ago. The company started out with a number of retired Bell engineers. I was the chief engineer at Bell for a number of years and retired 2003. I brought together a team of about 5 engineers that had a great deal of experience with the V-280 and the UH-1Y and Z, the current basically modern aircraft in the Marine Corps. And so we started AVX looking at a small coaxial rotor helicopter for the commercial market. The configuration that we have evolved over the years is referred to as a coaxial compound helicopter. Basically, nope, that's not it either. I can also brief that if necessary, Abe, having worked with Abe for a while. The coaxial compound is a configuration that is basically has the low disk loading characteristics of the helicopter, the low disk loading lifting capability, the low speed maneuver capability of a helicopter. And in fact, our configuration actually has a smaller footprint than the current Black Hawk or Apache legacy helicopters. The concept of compounding the helicopter is certainly not new. However, the way we're doing it is new. We've taken a coaxial rotor for lift, and we've added dual ducted fans at the rear, which provide us propulsion and also give us, by changing the thrust differentially, we can achieve yaw control, which solves one of the historic problems of coax rotors, which is if you've flown one in a descent, they do not have good directional control. We do in our configuration. And our configuration is built around a box, if you will. It will carry 14 troops in somewhat more spacious room. The seats are spaced on 26-inch centers, 24-foot wide. I think that's almost what you get in first class on most airliners. But these troops, of course, are wearing a lot of battle gear, and average troop we're designing for is 335 pounds, including the equipment he's carrying, so it kind of gives you a reference there. This cargo compartment is the same size as the V-22 has, And it allows you to carry, as I said, 14 troops. It allows you to load 2 463L pallets. Has flip rollers in the floor, so it's a cargo helicopter as well as a utility troop carrier. You can load 12 litters in the aircraft for medevac. And it has the capability to fly 230 knots because of the dual ducted fans providing propulsion, and to self-deploy if needed 2,100 nautical miles, which is the longest self-deployment leg from California to Hawaii. Of course, you have to put in auxiliary tanks to do that, but then any aircraft going over their rotary wing at least is going to take aux tanks. The configuration is going to reduce acquisition costs through the use of technology. We have some unique manufacturing concepts for the fuselage and other airframe components. The aircraft is all carbon fiber. It is all bonded together rather than mechanically fastened. One of the things we learned in dealing with composites was that if you mechanically fasten them the way aluminum is built, you end up with a very expensive piece of carbon fiber structure. So we're going to a lower cost method of manufacturing for the acquisition side, similar technologies in the rotor system and the fans. We would expect to see a significant reduction also in O&S costs because of the combination of the with the fans providing the propulsion. The rotor is truly loafing in forward flight. We have small wings, canards on the fuselage, as well as the horizontal tail that provide about half the lift at high speed. If you're at 230 knots, half the lift to overcome the weight of the aircraft is provided by the airframe and half by the rotor. And so your rotor at high speed is not having to propel the aircraft. It's just sitting there acting like it's a rotating fixed wing, if you will. The transmission is only operating at about 25% torque, so the bearings and the various components in the transmission are also very lightly loaded. And the real work is being done by the fans, who are in axial flow, so it's a little bit like a tilt rotor where you have a prop in axial flow, and you have less wear and tear on those transmissions. From a utility standpoint, the aircraft has common airframe and dynamics between the utility aircraft and the attack aircraft. The attack aircraft has all the weapons internal to the aircraft. They're on racks in this 6 foot by 6 foot, 18-foot compartment. They lower down out of through the belly of the aircraft or the floor of the aircraft through weapons bay doors. You only deploy them when you're ready to fire, so that if you're cruising out at you can cruise out at 230 knots, same speed as the utility bird, and that's of course a significant advantage you don't have today, where the attack aircraft with stores on the wing is slower than the utility aircraft. So the enemy also doesn't know what's coming at him. He doesn't know whether it's a bunch of troops inside the aircraft or it's a heavily armed attack aircraft capable of shooting back. And I'm down to 1 minute, and my charts have never come, so I've spared you that.
You did great with that.
And thank you very much.
Sorry, apparently my use of the timer knocked out the slide capability, so I apologize for that. So next we have Bob Hastings, who's the Senior Vice President. Here's your slides, of course. And here, okay, we've got your slides for you, Bob. So, the Senior Vice President for Communications and Government Affairs and the Chief of Staff at Bell Helicopter, also a retired aviator and lots of experience both at Bell and here in the Beltway. So you want to talk about what Bell is?
Sure. So again, I also thank you for the opportunity to be here today to talk to the audience about something that we're really excited about. Go ahead to the next slide. And skip to the next. So our offering into the discussion in Joint Multi-Role Technology Demonstration is what we call the V-280. It's a third generation tilt rotor. 280 comes pretty simply in the design here. When you tune the rotor for 6K95 and rotate it forward, you get 280 knots. And so early on, our modeling indicates that that's easily achievable and probably easy to exceed. It is third generation, so we see this as probably the lowest risk approach to a leap ahead capability for Army aviation because it's based upon tilt rotor research that we've been doing for more than 50 years. It's advanced technology. I'll show you in another slide. Reduced complexity. We've taken a tremendous amount of complexity out of this. It's in the V-22 that's there for all the right reasons. Significantly lighter, and you'll get a significantly reduced cost out of that. Next chart, please. This is just one example, and my apologies if you can't read all the writing in the lower left. But here's just one example of where we're working to reduce parts, complexity, and assembly time to get you more affordability. We think it's about a 30% cost savings against a V-22 that would be built at about the same size. And if you look at the columns on the bottom, the count of parts in the wing skin, the tool count, the weight, detailed components, all of those things, you can see a significant difference between what's in today's V-22 and what's in tomorrow's V-280. And a lot of that has to do, I talked about the V-22 designed for a very specific purpose with technologies that were available back in the 70s and 80s. A lot of the restrictions that are around the V-22 designed in order for it to work off the Navy and Marine Corps ships are not in this, so we're free to be a little more creative in our designs. And we also have a number of years of experience in advanced technologies, carbon fiber and related things. So you'll get this just one example, significantly less complexity and significant savings both in cost and weight. Next chart. But here's what tilt rotor really does. Tilt rotor gives you speed, and I know there's a lot of debate as whether speed's worth anything at all, but speed gives you range. And range within time is a real advantage on the operational battlefield. So if you look on the right-hand side of that chart, the left-hand where you're looking at it, you'll see tilt rotor compared to an H-60. And so that's a range ring if you superimpose it over where they're operating today. And if you take a look on the right-hand side, an air assault mission moving an infantry battalion, you can do it with 19 V-280s, 5.5 hours, less than $1 million total cost compared to Blackhawks, which would be almost $2 million in 8 hours to do. And that's really around speed and range. You get a savings from not only less time in the air, but if you look on the chart, you'll see there's no FARPs. Because if you're flying twice as far and twice as fast, you get additional savings outside the aircraft itself. So you don't have FARPs on the ground, you don't have troops in the FARPs, you don't have security on the FARPs. And so the compounding of savings goes well beyond just the manufacture and acquisition operation of the aircraft. Next chart. So let's talk about the Pacific for a second. Again, those are range rings on the Pacific side comparing a current medium lift aircraft to the V-280. You can see you can pretty much move up and down the entire Pacific coastline there. And again, if you look on the right, self-deployment, it's 2,100 nautical miles. That's exactly the right figure. It's the longest leg anywhere in the world. So with a 2,100 nautical mile aircraft, you can deploy anywhere. This just shows it in the Pacific. The advantage you get to that is it kind of unhinges the Army from strategic lift. So if you look at an organization like the 82nd Airborne that has to move somewhere, today they use about 1/3 of their strategic lift moving Army aviation. You give that strategic lift back to the commander, and Army aviation meets them at some intermediate staging base or forward staging base. They just get up and go, and they meet the troopers when they're there. As a side note, out at the Singapore Air Show last year, we had a couple of V-22s there. Lieutenant Colonel, squadron commander, he had V-22s operating from Australia to Singapore where he was at. He had a couple in Japan, and he had V-22s operating in the Philippines. And that was the operational scope of a V-22 squadron. And that's completely different thinking than the way we're looking at things today. Next chart. So take the same thinking and apply it to a future or current operational regime like Africa. Skip to the next chart just for a second. This is how big Africa is. This really caught my attention when I saw this. It's from a Marine Corps presentation. The United States, China, most of the Middle East, and most of Europe all fit onto the continent of Africa. So back up just a second. So here's what you can do if you went into operations in Africa with Tiltrotor. And this is based on the V-22's capabilities. But you can see the first ring is current medium lift helicopter, second ring is current heavy lift helicopter, and the 3 outer rings are what you can do with a tilt rotor, depending on how much fuel or whether you have the ability to aerial refuel. So it gives a commander tremendous operational reach that you don't have today. Next chart, one more. That's just a quick chart to show we are looking at this from a joint perspective because it is a joint multi-role. Significant conversations ongoing with the other services, and we're looking at making sure that we can develop an aircraft that meets everybody's requirements. It will be a complex problem. We've talked about that this morning. Next chart. So summarize, speed, range, and payload. Range being the key operational factor there. It is third generation clean sheet. Everything we're putting into this is designed brand new, based on experience, but it's new designs. I think it gives you the best value. Fuel efficiency. I'd be remiss if I don't remind everybody that a tilt rotor becomes a turboprop, and the wing does the work. And so as a tilt rotor flies faster and faster, it actually uses less fuel. And that gives you significant savings. Double the operational reach, and if you start looking at things like logistics, security footprint, and medevac, and that strategically self-deployable capability, I think you get a tremendous capability that can give us a lot for many years in the future. Thanks.
Well, you guys are doing wonderfully. You're beating your times. Well, in an effort to confuse you, we're now going to go back to a coaxial rotor design. Pat Donnelly is the program director of the Future Vertical Lift Prototype Program for Boeing, the Boeing Sikorsky team, and he's working with Sikorsky to do that from Boeing. So you want to talk about your...
Sure, thank you. So I'm proud to be here representing the Sikorsky Boeing team. As you said, Dr. Lead, we too have a coax aircraft. Our coax is different than what Troy described earlier in many areas. First off, our rotor system is a hingeless rotor, stiff in-plane rotor. What that does is that provides better maneuverability, better handling at the rotor system. But it also allows us to reduce the height between the two rotor systems, which reduces aircraft drag. Certainly, as Bob described, JMR and Future Vertical Lift Medium, the goal there is long range, high speed. We believe that our aircraft does that from many aspects, but without compromising low speed maneuverability. So it'll operate like a helicopter when you want it to operate like a helicopter in the landing zone, but it also provides the speed and range of a tilt rotor. In our case, the Sikorsky Boeing team is benefiting from what was done not only back in the late 70s, early 80s by the HX-59, but most recently the Sikorsky flew the X-2, which is what the basis of our vehicle is, the X-2 technology. As we move forward, what we learned in the X-2 will be demonstrated this fall on the S-97 by Sikorsky. And then our vehicle will follow that. JMR, we call our demonstrator the Defiant because we are going to change the way people think about aircraft. Our Defiant has, unlike Troy's ducted fans, we have a large propulsor in the back. But our propulsor is unique in as much as it also can variable pitch, to the point that we can actually provide negative thrust. So we could slow down, use it as an air brake. We can accelerate it up. We can actually clutch it so it'll stop when it's in the LZ, so it's quieter. It's safer to operate, and yet with that reverse clutch, with the negative pitch, our aircraft can also operate with a nose down attitude and a nose up attitude for pitch pointing when we're in the attack aircraft. So we're very excited about this aircraft. We know that we will demonstrate more than 230 knots in 2017 when we fly, and we'll be building an aircraft that's the operationally relevant, technically relevant size. So the X-2 demonstrated the concept. Our vehicle will demonstrate that our vehicle can satisfy the needs of the U.S. Army.
Wow. Awesome. You guys are doing wonderfully. All right, let's see. Ben, you are not allowed to take the rest of his time. Last but not least, we have Ben Tigner, who's the Director for Advanced Systems Programs at Karam Aircraft and the JMR-TD Program Manager there as well. So, Ben, about the Karam design.
Thank you, Dr. Lead, for inviting us to participate, and thank you, Dan, for introducing the program. So, as Dan said, the JMR-TD program is based on the government's assessment that future Army operations are going to require capabilities well beyond what today's helicopter fleet can deliver. Our entry into the JMR program is the UTR-36. It stands for Utility Tilt Rotor with 36-foot diameter rotors. It is an optimum speed tilt rotor, which represents a fundamentally different approach to tilt rotors from previous generations. What makes it different is that the rotors are very, very lightweight, very, very rigid. They're not articulated, and they're capable of wide range speed variation, which gives it the ability to build additional efficiency both in hover and forward flight and remove some of the design compromise that traditional tilt rotors have between the need to be an efficient hovering rotor and an efficient forward flight propulsor. So we hover with the rotors vertical, and then we transition into forward flight with the nacelles horizontal, and then we're in axial propeller mode flight with low vibration and high efficiency. So this really brings it combines the capability of a high-performance turboprop without sacrificing any of the landing zone agile maneuverability of a traditional helicopter. And in fact, it's in edgewise flight and in wing-borne flight, it's far more maneuverable than a conventional helicopter. Now, the efficiencies of the configuration and the tight integration and the low-cost manufacturing approaches result in a system that, despite the fact that it has substantially more capability than current helicopters, also ends up being about half the operating cost on a per-hour basis compared with conventional helicopters. So, next slide, please. So our approach here is to take a few nuggets of technology that we've been maturing over the past decade and combine them with design elements which, while somewhat novel in their application of rotorcraft, have been extensively vetted and deployed in other contexts elsewhere in aerospace. And the result is a solution that really substantially closes the performance gap between fixed-wing airplanes and rotorcraft, but without sacrificing any of the wonderful low-speed hover handling qualities of a helicopter. So the key marquee technology here is the optimum speed tilt rotor, the ability to vary the rotor speed and build efficiencies. This is something that we've been developing under extensive $25 million worth of internal private investment, together with extensive government investment in the form of the Joint Heavy Lift Program from 2005 to 2010, and also in collaboration with other government activities, for example, NASA's LCTR, large civil tilt rotor, that shows that this technology is eminently feasible, eminently achievable, and all of our analyses are overlaying very well between us, between the government and our industry partners to show that this is absolutely on track. Individual blade control is another technology element that we add that eliminates the single point failure associated with the swash plate control mechanism on a conventional helicopter. That's probably the single most challenging individual element. It's very, very important because the individual blade control actuators need to be extremely reliable and extremely fault tolerant, and we're well along in the development of those, and we're very, very confident. We're using a multi-speed transmission to increase the efficiency of the engine across a wide RPM range. Now, we also bring very, very efficient aerodynamics into the puzzle. The fuselage is efficiently designed. It's a very efficient high aspect ratio wing. The rotors are very, very carefully designed, and they all function very, very well together. We bring a pressurized cabin. We can cruise at up to 45,000 feet when the mission calls for it, so you can have the ability to get above weather and above man pads and other threats. But it's also efficient cruising at low altitude as well. We bring substantial crashworthiness improvements over conventional current generation helicopters. We have no heavy machinery on top of the cabin. There's good separation between the fuel and the passengers. If a rotor should be damaged in battle or for other reasons, we have the ability to shut down one rotor and continue long-range cruising flight on the wing with one rotor shut down and one rotor turning. The bottom line, the end result of all of this is that we have an aircraft design that carries twice the payload compared to current generation Blackhawks. Carries twice the payload. It carries it at twice the speed. So that's 4 times the basic aircraft utility. But it does it, because of the efficiencies of the aircraft, it does it at about half the operating cost. So that's a factor of 8 total improvement over current generation rotorcraft in the overall cost effectiveness of the system. Next slide, please. Now, speed is really important, and persistence is really important because they both affect response time. If you want to say that you want to be able to respond to a request anywhere in a country the size of Afghanistan in 20 minutes, we can do that with our speed with just 4 aircraft. Now, response time is important in the context of attack. It's also important in the context of medevac and other kinds of utility-like missions. We have a very high degree of commonality between the different variants. The JMR program asks us to focus on the utility variant, the UTR, but we also have a strong interest in the ATR, the attack variant. Everything above the intersection between the fuselage and the wing is 100% common between the 2 variants. So the wing, the rotors, the drives, the propulsion, the fuel system, the controls, 100% common in terms of logistics and training and hardware. And what's below that intersection is, we call it a mission pod. It's a mission specialized element of the vehicle. And what that points out is that once you have that wing and the rotor developed, then you're not limited to just 2 variants. You could, in principle, have even more variants. Okay. Okay. So next slide. All right. Future theaters of operation are going to favor vehicles that have very, very long self-deployment ranges. We're talking, our analyses are showing 6,500 nautical miles of self-deployment, but we also fold up and go on the LHD and LHA. Next slide, please. The rigid rotors give us very good agility in the landing zone, very good ability to accelerate away, and fluidly transition back and forth between rotor-borne flight and wing-borne flight. This configuration, not only does it accelerate very quickly, it also decelerates very quickly. So just 20 seconds for the next 2 slides.
All right, that's it.
Okay, so our approach to the JMR program is to build a 100% scale version of the eventual deployed aircraft, and that means that we have a direct line from the measurements into predictions of the capability of the next airplane, and the next will be my last slide. And it's widely accepted in rotorcraft that scaling up is very hard, scaling down is very easy. We started out at the JHL size, the TR-75, and our UTR-36 is a significant scaling down. We know it works at the large size, and therefore we're in very, very good shape for the small size as well. Okay, thank you.
All right. Thanks very much to all of you. Appreciate your comments and in particular the brevity of everyone but you, Ben. But you did only went a little tiny bit over. Dan, if you wanted to offer a few concluding remarks and then we'll get to the Q&A, that'd be great.
Okay, sir. So I'd like to leave you with an information that FVL is real. It's evidenced by what you see here, right? Joint Multi-Role Tech Demonstration. Industry and the Army is investing a significant amount of money in a system-level S&T demonstration, which we have not done in generations. We have a huge opportunity here to set the stage for the next generation of vertical lift, and it's real. We're executing as you see today. So I'd like to thank all the vendors because they've done a great job. They all have very relevant designs. They're all working hard towards an eventual build and flight test. Unfortunately, we're at a critical point in the schedule that you saw earlier where I'd love to take all 4 forward to full flight test, but financially the resources do not allow us to do that. So we are at a point where we have to make a descope decision. We are in that process now. We hope to make that descope decision within the next 30 days or so and get the industry partners back on track at some level. So what that means, though, is although we will descope to something less than all 4 to fully flight test, that should not represent that any of these vendors have an unviable design or configuration or opportunity for the future. So that's important to understand as well. Flight tests will be in the late 2017 timeframe, according to our current schedule, which nests well with, from a program of record perspective, an anticipated material development decision in late 2016 with an analysis of alternatives in 2017. Nesting both of those together is really the job that I have, and that's transitioning, as you can see, both the S&T effort for the air vehicle and the mission system architecture piece into a program of record, so we understand up front not only what technologies are available, but how we go about acquiring them efficiently. So,
thank you. I want to ask just one quick question about, Dan, you were very emphatic that this is going to happen. They're tough bets to make these days. And given that this is sort of the first edge of essentially at least at this point, the game, in the future game in rotorcraft, I wanted to ask each of you for your perspectives on what the JMR and FVL efforts mean in your minds for the industrial base as a whole, for the kinds of STEM development that I think is a broad national concern, and sort of ask you to, if you were a senior policymaker, apart from your parochial interests in this program, can you describe the importance of it? Because I think sometimes that gets lost and drowned out by similar arguments. So, any of you want to speak to that?
Sure, I'll start.
Okay, great.
So JMR in the near term really invigorates again the opportunity to design an aircraft from the ground up. We've been very conscious to establish a team where 40% of the team has less than 10 years experience in the industry. Really trying to bring that young mind, young opportunities, different way of thinking. Certainly in the long term, you know, FVL medium is identified as a very large program. You know, the Sikorsky-Boeing team right now has the Black Hawk and the Apache production lines going, satisfying the near-term need for this mission. And as we transition, certainly it would be a significant continuation of that industrial base, not only for the OEMs themselves, but the whole supply base, just to continue this aircraft and provide a great opportunity.
So I'd take that exactly correct, but I would add just a little bit more. If you look at the DoD strategy going forward, and in particular the Army's view on that, technology insertion is going to be absolutely essential. You're not going to be able to do in the future what DoD and the Army are envisioning without some kind of significant step change in the technology to enhance that. So the Air Force has got significant technologies under development. The Navy and the Marine Corps both are doing that. And I think the Army has to be there, or they'll be trying to do very different missions in the future with aircraft that were designed long ago. And there'll be incremental improvements at best. And so I think from both the national security perspective and the industrial base, it's absolutely essential that we stay on track and fund these things.
Let me add one thing from an operational perspective. You saw a lot of charts earlier that I think set the stage. You know, vertical lift from the time of inception has changed the way the war is fought, right? Across the sea, across the land, does not matter. Envisions operational environments of the future will just require that more. So when you think about the future in urban areas that we're going to be operating in, a vertical lift capability is absolutely essential. Having a vertical lift capability that's efficient and distributed in a fashion that you saw on charts earlier really revolutionizes the way we fight our wars. And if you think about that for just a minute, if we do not take a leap ahead in our vertical lift, then we are going to be behind our adversaries from that perspective. Very critical.
Yeah, I wanted to augment what you said. Other countries are moving aggressively forward, and we need to do that in order to not fall behind. Dan, you put your finger right on it. It's been a long time since the rotorcraft industry has been challenged to produce generation after generation of improvement. You know, we've been doing incremental improvements for a long time, and you know, we slowly lose the ability to generate revolutionary steps in favor of evolutionary steps, and this is an opportunity to reinvigorate that, and that's, you know, it's extremely important.
I'd add that AVX is a small company. One might ask, how would you play in this in the future vertical lift? For our tech demo, we have formed a team of 15, maybe 15, 16 companies scattered across the United States that specialize in rotors, transmissions, airframes, and so on. We have some large companies that do the cockpit and the engines and so on. But one of the things we bring besides a technological innovation to rotorcraft is perhaps a innovation in business structure. We are trying to become a virtual OEM, rotorcraft OEM, and not necessarily using the same business approach that the OEMs use. And so from a competitive standpoint and a cost standpoint to the U.S. government, we could very well bring a very different level of cost competitiveness going forward, as well as innovative competitiveness. So small companies team together can create great benefit for the military.
Okay. All right. We've got microphones. We've got here and then up front.
Good morning. George Nicholson. I was the senior director of the analysis of alternatives at U.S. SOCOM for the CV-22 Osprey. You talk about the self-deployability. One of the issues, like when we sent 4 CV-22s down to Mali 3.5 years ago, it took almost 3 days to get down there. When the Marines sent their MV-22s from Okinawa down to Townsville, it took almost 2.5 days. We've got capabilities in SOCOM like the Silver Bullet package at Fort Campbell, Blackhawks. We can put those anywhere in the world in less than 24 hours because we can put them in the back of a C-5 or a C-17 and get them there. So a question in terms of, you know, all 4 manufacturers, is your capability going to have the ability of putting it inside of a C-5 or putting it inside of a C-17?
Anybody want to?
I think I'd start with saying that's not one of the requirements that's been articulated. Right, so we could build and design whatever the Army's asking for. They haven't asked for that. So self-deployment is really where we're focusing on. So I'll tell you, in recent years, though, you'd see a much more rapid response from the V-22s when they self-deploy because it's a mission that they're used to doing now and the resources are in place. So the V-22s that went into the Philippines went 1,400 nautical miles to get there. They were the first aircraft to arrive on scene. But for JMR, it's not a requirement that's been articulated.
Yeah, so for JMR specifically, we have not set all of the requirements that would be of the program of record, obviously. We went in with an understanding of the capabilities that we're looking for broadly. It's focused on the air vehicle piece from a performance, speed, payload requirement. So that's really what we're trying to innovate on. Again, remember, these aren't the prototype aircraft, they aren't the solution, but they demonstrate the enabling technologies of that configuration in a more efficient and effective and affordable way than we've done it in the past. That's the key part of it. But to get to the deployment piece of it, it's a doable in a smaller package to burden the strat air piece, meaning C-5, C-17s, to take a small contingent somewhere. If you think about the aviation brigade of a conventional force, it takes a significant amount of strat air to get those there. So you would not take a aviation brigade team today and send them on a C-5, C-17 in 24 hours, right? It would take you weeks. And so what we're still, even if it takes that future vertical lift aircraft 2 to 3 days to get to this long-range deployment, you would still be well ahead of the cycle time that we have today to get a brigade combat team somewhere.
I sort of think of the JMR-TD as kind of the concept car of where FVL is going, and
very good analogy.
That helps me sort out the few. Here, and then we've got some in the back.
First of all, let me say with these ranges that we were talking about, you will deploy faster than any C5. So that's my answer. But back to your question, you're posing a doubt about the program. And we look at rotorcraft, and they were at about $2 billion a year in 2011. The industry very quickly went to $12 billion a year. We may shrink down, but we don't want to go back to $2 billion a year. So if we stay with the current vehicle type technology, we have no justification to continue, and their production lines are going to stop at a certain point.
Right. Well, and I think my question was trying to get at not just the level of activity, but also the qualitative content of it, right? I mean, I was having a discussion before we started with Troy about how he's got some 85-year-old engineers and some sophomores in college, right? And again, from a national perspective, how do we get those sophomores to become the people who are sitting on the stage 40 years from now? And that's again both a quantitative. There's a quantitative element to that and a qualitative element as well. So, okay, go ahead.
Hi, I'm Richard Whittle. I'm here today for Breaking Defense website. And I wanted to ask you, Mr. Bailey, if you would go into a little more detail about how what I might call the musical chairs phase works here. I think you said that within 30 days you're going to down select, but you didn't say to how many entrants. Would you explain why you're not saying how many? How's that decision going to be made? And then how long will it be until you do another down select, and will you ultimately, when will you get to one entrant?
Okay. So there's a lot of detail in that question. Thank you for that. Number one, I wouldn't call it a down select. That's been a term used in the past. This is not a FAR type of Federal Acquisition Regulation type contract. We are all in partnerships. So we have vehicles, contract vehicles called Technology Investment Agreements. Those are truly agreements. They're cost share arrangements that allow us, from an S&T perspective, the government and the industry to partner and to share the cost of development and innovation. That's how all of this is arranged. So I wouldn't call it down select first. So I called it descope, and the reason why I called it descope, when we initiated these TIAs last year, we negotiated all the way through fiscal year 19, all the way through the flight test with all four. So all four vendors are on those TIAs with the full scope. We understood then, and the industry understood then, that we did not have the financial resources on the government side to resource that entire time for all four vendors. So it's always been the strategy and the plan that we would have to descope to something at this time. What we do know, and our base strategy has always been, that we have enough funding to take at least two completely through our full flight test program. So that is our base strategy, has always been our base strategy. That said, we are certainly looking to further our information and our best return on an investment. So what that equates to, I don't quite know, and I can't tell you exactly the details of our process that we're going through right now. What I would also offer is the industry has, and we have shared publicly, the 5 criteria that we use for the decision. Basically, at a top level, those criteria are: what's the S&T gain for doing something with each vendor? Meaning, what do we learn and what do we gain? How close and efficient does their design meet the model performance spec, which was our snapping the line of the requirements that we provided to them to design towards? How well does their demonstrator aircraft validate the enabling technologies of that model performance spec? so far to date have they executed on schedule and on time, so we have confidence in their management going forward. And then, of course, the last one would just be the overarching programmatics piece of it. Do they have the capability and the skills and the competencies by which to do such a demonstration? So those are our 5 top-level criteria. Below that, there's a lot of detail. The industry partners have done a good job of last week back briefing us on their plans under those criteria. So now our government team is in the process of sorting through all the information to look at the best return on our investment. So the resources we have, we in turn plan to get as much as we can out of that. Exactly what that looks like, I can't tell you today.
And then, if you could, when do you get to 1 aircraft?
Well, again, there's no plan to go from JMR-TD to another D-scope. JMR-TD, the system level demonstration will end. Right now it ends in fiscal year 19 with the flight test completing. Now there's ongoing science and technology that will continue, is going on now outside of JMR-TD, and that will continue. Will we be able to continue the air vehicle demonstration past fiscal year 19? That's dependent on resources, of course. But the anticipated path at this time is that the demonstration we are executing now rolls into a new competitive acquisition for future vertical lift. That is an open intent. The acquisition strategy is to take what we learn, put a new specification together based on the requirements that we see and the capabilities that we anticipate under our demonstration. That will go out to a broad solicitation, and just like any other acquisition program, we'll execute a new strategy with a new vehicle. Okay.
Over here, and let's go, Heath, let's go here, and then here, and then there. Sorry. Be fair.
You know, Otto Kreischer with Sea Power Magazine. One from Mr. Hastings. You first said that your model doesn't eliminate some of the complexities and costs of the Marine and Navy version, but that at the same time you offered a folding wing capability, just like the current Ospreys have, which is one of the big complications. So maybe you could explain, where you're minimizing, the Marinized versions, the Marines are currently using with the Tiltrotor thing. And the other one, on your for all of you, on your self-deployment figures, you're talking empty aircraft or with your troops on board?
Yeah. So the fold capability of the V-22 is just one of the features in the V-22 that will be less complex going forward. So the Army, what we're building in JMR, the technology demonstrator, will not fold. It's not a requirement. The other services are talking to us about that. So that could be in some models. But we also have things like the transmissions and the engines in the V-22, the whole nacelle tilts, that's out. The size of the rotor is designed today on the V-22 to match its ability to fold and fit on the elevator. So those requirements are out. And then just manufacturing, our engineers over the last 20 years have learned a lot of different ways to build things and put them together. So if you looked at that one chart that talks about how many parts that are different, just parts and tooling, there's a significant savings there. So it's not just the blade foldability. And on the self-deployment, in our model, for the 2100 nautical miles, it does not carry troops. It's got internal fuel for that self-deployment.
At a top level, the requirement set was to get the aircraft there. So they have the option of putting additional internal fuel cells in place, right? The intent's not to fly directly into the operating environment with the self-deployment configuration.
Good morning, ladies and gentlemen. My name is Rosemary Seguero. I'm the president of Seguero's International Group. I'm a USA-based company, but I come from Africa, from Kenya. Looking at your presentation, how do you looking at the technology and affordability and training? How do you see the African military buying your helicopters, and are you going to train them, or do you think of manufacturing them in Africa, or what would be the best way for them looking at affordability and learning? And definitely they'll buy the planes. And lastly, how do you look at the evacuation? Maybe in future you look at evacuation helicopters in case of war or emergency. How do you look at that in future? Thank you.
So I think the ability to export the aircraft and foreign military sales is way on the horizon in the timeline we're developing here. So what we're really focusing on now is a technology demonstrator for the Army requirement. I think it's probably well after Future Vertical Lift is competed and somebody's selected before we can even begin to entertain how that would be sold around the world. I will tell you though, for all of us, once you get down to building an aircraft in the numbers that this Future Vertical Lift promises, I think there'd be a very robust foreign military sales and potentially even commercial applications off the technology once it's being built at that rate. So unfortunately, I don't think I got an answer in the short term for you.
Hi, Jen Judson with Inside the Army. The technology demonstration is happening likely smack in the middle of implementation of full sequestration. So I'm wondering what you're doing to plan for that. What's at stake if we are facing full sequestration in 16, 17, 18, 19, the years that you're going to be doing this? Can you talk about how you're trying to protect the program? And also, for you guys, how much are you willing to commit in terms of cost sharing to keep this going?
I would offer that although sequestration is a potential and likely, that across the Department of Defense, I believe you hear the continued support for both research and development. So from a science and technology perspective, I have full confidence that we are not at risk. The focus, to be honest with you, in this cycle from the senior leadership is to focus on science and technology. Now, they want to ensure that that focus is prioritized, and the Army has done a lot of work in the recent past here to focus the priorities of science and technologies. So honestly, I would tell you I don't have many contingencies because I do not feel at risk that the JMR-TD will lose its resources.
I think if I could speak, I think as Dan described earlier, we're all under a TIA. And in the TIA, the expectation originally was that it was at least a 50-50 cost share. And I believe, speaking from all of us, we are investing more than the 50% cost share that was requested. We're all under contract to design and build and fly the aircraft. So, Dan's got the terrible task of telling a couple of us, perhaps, that we aren't going to go forward. So at this point in time, I think industry has committed the resources necessary to fly those aircraft.
Yeah, we're very confident that we can execute and fly this airplane with the resources that are available.
I have another question about sort of positive externalities from the program. A number of you have raised improvements in manufacturing and other things, and I'm wondering the degree to which those can be exported to other efforts, either commercial or military, and what are there other areas where those kinds of advances are being made that can be harvested, so to speak, and elsewhere?
So I will let them talk the details, but I would offer, in the science and technology area, we've of course got a lot of partnerships, industry and commercial as well, and we were looking at all of those. We are, in this constrained environment for resources going forward, we are certainly looking for synergies. We are looking for where there is redundancy so we can reduce those redundancies. On the acquisition side of the house, I would offer to you, as I said earlier, what a Future Vertical Lift initiative gives us really is an opportunity for a clean slate innovative acquisition approach. And that branches all the way into manufacturing. So I actually have a study group under the acquisition effort that's looking at the manufacturing part of this. We're tied into what's called a digital manufacturing and design innovation, which is a presidential initiative under the Advanced Manufacturing Enterprise. And we're partnering with them, and our industry partners are partnering with them through the Vertical Lift Consortium. So we're looking at all of those opportunities to bring the innovative approaches that you really can't employ on a legacy fleet that we have today, right? And under that, if you will, I believe there are plenty of international and commercial opportunities that will play out in this going forward. I know that the industry has some examples.
So rotorcraft have struggled to a certain extent, and because of the relative productivity and cost effectiveness and frankly safety level of rotorcraft relative to fixed-wing airplane, rotorcraft have never been able to penetrate the commercial transport markets in the way that fixed-wing airplane and it's been a long-term goal of ours to try to completely close the gap in all of those areas, including safety, including cost, including utility, and speed between rotorcraft and fixed-wing aircraft. And we believe that we're really focused on the JMR-TD and delivering this specific solution, but this clearly plants a seed of commercially viable transport, VTOL transport in the next generation, and we're very excited about that prospect.
Yeah, the technology that we're using with our TD is very definitely transferable to other rotorcraft. Could be used on a tilt rotor as well, or commercial world. It's, I mean, there's a lot of technology that's going to spin off from this Future Vertical Lift program.
Rudy Osich. This technology demonstration program is obviously focused on the Army's Black Hawk and Apache utility attack aircraft, both of which are manned systems. Innovation in today's aviation world is in the unmanned realm. Requirements will probably change over the time of this program because it's not scheduled to deliver until 2030 or 35, or maybe 15 or 20 years down the road. And so it's hard for the requirements community inside the Army to define what they really need that far down the road. But should this effort move and should requirements evolve so that you would get away from manned systems into either optionally piloted or unmanned systems, how would this affect your design approaches? Would all four of these approaches be malleable? Would they be able to be mutated or somehow adapt to an optionally piloted or unmanned configuration?
I think all four of the companies have designed their vehicles to be optionally manned from the very beginning. So that's sort of a foundational piece. Our tilt rotor, as I mentioned, is very modular, where the wing and the rotors are one unit, and then the fuselage, we call it a mission pod, is another unit. What that means is that in our case, once you have the wing and the rotor, the propulsion part, you can come up with all manner of different systems using that basic building block. So we envision unmanned variants. We envision variants that have a much larger fuselage and carry more passengers. So yeah, unmanned is definitely in the sights, a very critical part.
Yeah, the basic requirement was optionally piloted vehicle, OPV. Now, exactly how that operationalizes, the requirements community is still working on conceptually. But I think the basic knowledge of these air vehicles lends itself to say that when you're talking 2030 and 2040 and beyond, all of these vehicles could go to an optionally piloted configuration very easily. The fundamental pieces of that is a flight control system that can be controlled through ones and zeros, right? All of these are fly-by-wire flight control systems. That's the advancement that we'll have. So the basic aircraft will fly that way, regardless if there's a pilot in the aircraft or not. The interface of that will be through a flight management computer, which would have fully coupled modes, right? So generally, if there's a pilot on board these aircraft in the future, the vision is really not that that pilot's flying it very often anyhow. And then the last piece will be an interface, whether that's a uploadable mission, autonomous flight profile that just it gets imported to the flight management computer and the aircraft goes fly it, or whether you data link it from a ground control station. That's the operational context that is not yet defined, but the air vehicle really won't know the difference. So I think all of them are able to be optionally piloted.
And a couple in the back there. Do him and we'll come here.
Hello, Mike Bosworth, Naval Sea Systems Command. The V-22 has had two issues that have been a concern, and we've been mitigating that with deck wash, and, downwash and deck temperatures. Are there any requirements in your multiple technology demonstration for those two things, and is there any comments on the concepts as how they address downwash and deck heating?
Yeah, so I'd start again by saying it's clean sheet design. So this is the V-280, so it's a third generation, but there's a lot of lessons learned off V-22. So to those particular things, the disk loading, we envision the disk loading in the 280 to be about the same as the Chinook. And the engines don't rotate. right? So that's where there's some concern about the tilting of the engines on the V-22. So the engines don't rotate in the V-280. It wasn't done for that, though. It was actually done, one, to reduce complexity, get a lot of cost out, and also for this to be a functional Army aircraft. The Army wanted the sides free and open for troops to enter and exit with full visibility, to be able to do combat action as soon as they step out of the aircraft. Both of those concerns, I think, are probably not of concern to us going forward with the 280 design.
With our airplane, we have about half the disk loading of the V-22, so the downwash is much less of an issue. And our configuration didn't show in any of the views, but we have quite a bit of separation between the nacelles and the ground. We can also have exhaust diverters if that becomes necessary.
Although we're cognizant of those issues, right? We did not want to go into a science and technology program with too confining of a box, right? So we want the industry partners to innovate and give us ideas and solutions that would be a best case, because there's always trades. So we did not define those specifically. We do have our Navy counterparts engaged in that in the process. They have ensured that Navy equities are involved and aware. So as an example, folding is not a requirement for the demonstrator, but taking into account folding in the design is, as an example. And several of the partners are looking at doing folding on the demonstrator just to show that it can, if there's a concern about it. So we didn't constrain it, but certainly all of the attributes are being looked at.
I have a related question from Roman Schweitzer at Guggenheim Securities. He says, given the money and time to work the full JMR-FVL approach, has the Army considered a spiral evolution of the V-22 design? How and why is that design deficient from FVL's needs, and wouldn't the Army benefit by getting an 80 to 90% solution much more quickly at lower cost? So you spoke to parts of that, but.
Sure. Well, that's probably a partner to answer. Again, the V-22 represents a set of requirements from a few decades ago. That was the efficient manner by which it was employed, and we gained those capabilities then. Today, it represents, we represent a new set of capability and requirements, and we're looking for a solution that gives us those capabilities, environments, and requirements in a much more effective, cost-efficient manner. So is that an incremental upgrade? I believe that the partners have shown you that it's really not. So, even Bell has looked at this from a blank sheet design perspective. And so gaining the kinds of capabilities we're looking at for the future in the affordable, efficient manner is not necessarily seen as an incremental upgrade of the V-22. Okay.
Good morning. My name is Tony Melita. I'd like to get back to Dr. Lead, your fundamental question regarding feedback or potential guidance to policymakers associated with what we've heard here. To me, I'll characterize it as kind of the elephant in the room, and to me that is the Army, and I understand the budget constraints, but is the Army going to make a budget-driven down-select or de-scope decision prematurely? Are we in a position under the auspices of future vertical lift in this country to potentially advance technology to a point where we can make more prudent business decisions? Are we making that decision prematurely?
Well, that's left to the beholder, I guess. Great question. Again, I don't believe that the descope that we are executing should be envisioned in any way that any of these designs aren't viable for the future. Of course, we would all like to continue investment across the board at the level that we are. So is it prematurely? I don't believe at this point it is. And the reason I say that is we have done a lot of work to date. So building and flight testing is not the only way that we continue these solutions, right? And honestly, building and flight testing is just the gold star of where we are today. We have come a long way in the last 5 years, I would offer. And I think industry would tell you that the tools and the personnel competencies that I talked about earlier are a critical driver for future vertical lift. If we're not building the prototype aircraft to flight test under JMR, then that means that we're going to sort of start over with program of record, if you will. And when I say start over, I'm talking about, again, we're going to be able to bring the next 5 or 6 years of advanced technologies into bear to the Future Vertical Lift program, whatever that first one is. The way we can do that is by having the tools and the personnel competencies available to do that. So the industrial base decay that we've been talking about has really been shored up over the last 5 years. Through the configuration trades and analysis that we've done and the work that the team's done in the last year on these designs have put us in a position where we can go to industry today and say, we want you to alter a particular aspect of your solution, and they can give us a solution feedback fairly quickly. The government team, which was not able to do this a few years ago, was able to take a smaller set of requirements from our requirements community, and in about 3 weeks' time was able to output various configurations of designs to meet those subset of requirements. And that's a capability we haven't had in the past. So as a program of record, I would look at it from the aspect that what we've done to date is already leap aheads of where we were 5 years ago. Building and flight testing something is certainly important, but not the only path for any of these solutions to continue. And when we get ready to do a source selection for an actual program of record, having the industry competency and the government team competencies that are in place today are going to be the critical aspect to make sure we have a program that's solid going forward.
Okay. Any other questions out there? All right. Thank you all so much for taking the time to come and talk to us today. We really appreciate it. We're looking forward to seeing where this goes. And thank you all for taking the time. Go USA. And hopefully we'll make it through the next round. Take care. I hope everyone has a good holiday.
Thank you for having us.